So one of the things we're concerned about with solutions is measuring the concentration. So a standard solution or a stock solution is a solution that's concentration is accurately known, meaning we know what the concentration is. There are multiple ways to measure concentration mathematically. There's percent by mass, which is very similar to percent composition, and you're familiar with this because that's what's on nutrition labels. Percent by volume, things like hydrogen peroxide and alcohols, your like isopropyl alcohol, rubbing alcohol at the store will usually tell you that it's 95% alcohol by volume, meaning that other 5% is water. Normality, which has to do with acids and bases. Molality, which is important for colligative properties. We're not really going to get into molality too much, but the one we're really focusing on in this unit is molarity. And this is the most common way to express concentration in chemistry. So a little bit more about molarity. It is the most commonly used expression of concentration. The formula to calculate molarity is moles of solute over liters of solution, so moles over liters. The number of moles of solute dissolved in a liter is essentially the word format way of describing what molarity is. It is represented with a capital M, and units are capital M, which stands for molar. So you'd say you have a 1.5 molar solution. So i.e., a 1 molar solution of aqueous sodium chloride measures 1 mole, which has a mass of 53 grams of sodium chloride, and add 1 liter of water. Now you may remember back when we did density, I showed you the little density triangle, and it was a way to remember how the formula worked, and if you were solving for something that wasn't density, how you could turn the formula around. I've recreated this triangle again for molarity, and you can use it the exact same way, where molarity is equal to moles divided by liters. But if you were asked to solve by liters instead, you could have moles divided by molarity. And if you were asked to solve for moles, you would do molarity times liters. So you just always cover up the one that you are solving for and then do the appropriate mathematical function. Now, something to keep in mind, you might not always be given your information in moles. You might be given in grams and you'll have to convert to moles. And you might be given your volume in milliliters instead of liters, and you'll have to convert to liters. But both of those are skills you already have. So once again, our formula is molarity equals moles of solute divided by liters of solute. So let's do an example together. If 5.7 grams of potassium nitrate was discovered in 233 milliliters of water, what is the molarity of the solution? So we need to convert grams to moles of solute and milliliters to liters, just like I was talking about before. So in order to convert our grams to moles, we take our 5.7 grams of potassium nitrate. We find the molar mass of potassium nitrate, which works out to 101.10 grams, equals 1 mole, which means we have 0.056 moles of potassium nitrate. As far as converting milliliters to liters is concerned, you just move the decimal place over 3, so you know there's an imaginary decimal place there. 1, 2, 3. So we have 0.233 liters. Once we've done those two conversions, we are ready to solve. So we have 0.056 moles of potassium nitrate, which we solved for above, divided by 0.233 liters of potassium nitrate, and that works out to 2 sig figs at 0.24 molarity potassium nitrate. Pretty simple, right? Just dividing one number by another, you definitely got this. So let's do some practice problems. You must show your work to be able to use your notes on the note check. If you do not show work for these problems, I am not giving you a stamp. So I want you to pause this video and solve the following problems. What is the molarity of a solution that contains 42 grams of potassium chloride in a 7.9 liter solution? Once again, pause this video and come back when you're done to see if you got the answer right. All right, you should have gotten an answer of 0.070 molar as your answer. How'd you do? If you got it wrong, make sure you're using the equation correctly. I put the triangle up here to help you out. If you got it right, let's try another one. I want you to pause this video and solve for how many grams of sodium hydroxide are required to prepare a 200 milliliter solution of 0.5 molar sodium hydroxide. So pause this video and come back when you have the answer. All right, you should have gotten 3.6 grams of sodium hydroxide. And one last one. Tell me how many liters of 0.85 molar solution of sodium sulfate contains 0.35 moles of sodium sulfate. Pause the video, show your work, and come back when you're done. All right, you should have gotten 0.41 liters as your answer. How'd you do? Hopefully you're getting the hang of this and you're a molarity master. So there's another type of kind of molarity problem you could be asked about. And let's try one together. You are asked, how would you prepare a 0.55 liter of 0.7 molar solution of sodium chloride? So you're being asked essentially, what would you need to do to make this solution? So the first thing that we need to figure out is how many grams of that thing we're going to add, because we don't have balances that tell us in moles, so we need to go to grams. So up first, we're going to multiply our liters by our molarity, just like we see on the triangle up above, to get 0.385 moles of sodium chloride. But then we need to convert that sodium chloride to grams. So we have our 0.358 that we calculated. We are multiplying it times its molar mass, 58.44 grams, to get 22 grams of sodium chloride. So our answer to this question is I'm going to have to add 22 grams of sodium chloride to 0.55 liters of water in order to make that solution. Pretty straightforward, right? It's just a different way of asking you about grams. So I want you to pause this video and show this one on your own. Just like our last problems, if you don't show your work, you're not getting credit on your note check. So I want you to tell me how you would prepare an 800 milliliter of 1.2 molar solution of lithium hydroxide. Pause the video and come back when you're ready to see the answer. All right. You should have gotten that you're going to add 23 grams of lithium hydroxide to 800 milliliters of water. So there's one more thing we need to talk about in this video, and that's something called colligative properties. So a dissociation factor is the number of particles a solute breaks down when it dissolves. A colligative property is a property that is dependent only on the number of solute particles present in a solution. So basically, it depends on the molality and the dissociation factor. Examples of colligative properties are the freezing point and boiling point of something, two things you're very familiar with. An increase or a decrease in concentration will affect colligative properties. For example, when concentration is increased, the freezing point is always lowered, and we call this freezing point depression. When the concentration is increased, the boiling point is always raised, and we call this boiling point elevation. Similarly, as the concentration, if the concentration decreases, the freezing point will go up, and the boiling point will go down. So which would freeze faster? A 0.5 molar solution of salt water or a 1.0 molar solution of salt water? The answer is a 0.5 molar solution of salt water will freeze faster because it is less concentrated. And remember, as concentration increases, our freezing point is going to decrease. So that means the lower concentration solution is going to freeze faster. which would boil faster. Well, the 0.5 molar solution of salt water is also going to boil faster, and that's because it's less concentrated. Remember, the more concentrated, the more the boiling point gets elevated, so the one with the less concentration is going to boil faster. Let's talk a little bit more about freezing point depression and boiling point elevation. So why do we salt the roads when it snows? Well, by increasing the concentration of salt in the water, snow, the freezing point of water is lowered. So you know that water normally freezes at 0 degrees Celsius, 32 degrees Fahrenheit. But by adding salt, that means it's going to freeze at a lower temperature, below that 32 degrees Fahrenheit, which means it prevents the ice from forming on our roads because it has to be a colder temperature outside in order for it to freeze. Similarly, why do we add salt to a pot of boiling water when we cook noodles? I'm sure you've heard your mom or dad tell you to add salt to the water when you're boiling it. Well, what we're actually doing is increasing the boiling point. So the water is going to boil at a higher temperature. This allows our noodles to cook at that higher temperature, which is going to make them cook better and faster in the long run. But when you're standing there waiting for the water to boil, it is actually going to take longer for the water to boil. So it may seem like not a good idea, but in the long run it is. All right, that's all I got for you. Come to class tomorrow with your notes ready to go.